Hello, this is Ian Vogelesang, and this is the video for demo number 5, measure read versus write. So this is the first example, which is sort of a real-life thing to automate a kind of a workflow that you might want to do. So let's look at the RAID version of this. And then firstly, I'd like to direct your attention to the steps that we can see. So each one of these steps represents a subinterval sequence. The first 5 are max IOPS, 100% read, 75% read, 50% read, 25% read, and 0% read. Then what we're going to do is we're going to repeat these 5 steps, but we're going to run at 90% of the IOPS that we got when we ran at IOPS equals max. The idea there is that when you run at IOPS equals max for writes, the subsystem is going to be in emergency D stage with no room left in write pending because you're writing as fast as you can. But when we run at 90% of max, then we're expecting to see a significant different response time for the writes. For the reads, for IOPS equals max and 90% of max, you're not expecting to see much difference. But for the writes, you expect to see a substantial difference. So let's go and look at the IVScript file. Here, the part where we create the workloads is very similar to what we did before. We've got one test host. We've got a subsystem that has 4 FMD LUNs going to a 7+1 parity group. We're creating a workload named steady on the 2 of the LDEVs, the instance that show up on port 3C, and 2 LDEVs on port 4C. So we're getting all 4 LDEVs, but we're splitting them across the 2 ports. We're running at a 4K block size with max tags equals 32. And then we're doing a loop where we run for fraction read equals 1, 0.75, 0.5, 0.25, and 0. And by the way, you can do this as a traditional C-style loop as well. The IVScript language supports doing for fraction read equals 1. Fraction read is greater than or equal to 0. Fraction read equals fraction read minus 25%. I'm sorry, in IVScript you cannot declare a variable on the for statement, so you got to declare it ahead of time. And there is no plus plus increment operator, so you have to say fraction read equals fraction read minus 0.25. You can't say fraction read minus equals 0.25. So we do an edit rollup all equals all, parameters IOPS equals max, fraction read equals, and then we put in the fraction read. And then we do a go step. But the difference from what we've done before is, in this case, we're turning measure equals on, which means that we run until we have seen enough subintervals to make a statistically valid measurement after initial transients have died down. So when we do measure equals on, or when we do a PID loop, we have to specify whether the source is workload data or subsystem data. And in this case, source equals workload. And then for source equals workload, there are a number of categories that you can select. We're selecting here overall, but you could select random or sequential, read or write, random read, random write, etc. When I/O is complete, they're posted in accumulators, and in this case we're going to look at the accumulator for service time. And then the accessor here is count, meaning that we're going to look at the number of IOs that were posted into the service time. And what we want is we want to measure the IOPS, and we want to measure the IOPS after the initial transients have died down. And we've seen enough, in this case, to have 95% confidence that we're measuring the IOPS plus or minus 1.5%. And we're giving a timeout value here. And then notice I've also included a max write pending change attribute, which means that the measurement during the measurement period, write pending can only change by a maximum of 5%. We could have also included min or max write pending parameters here as well. And then here, look at this statement. If last result is not equal to success, then exit. Last result will tell you what happened for the last time we ran a go. And if it times out then the result of the test step will be failure. If it's successful, then you'll get success. So this says stop running the IvyScript program if any one of these steps for the different fraction reads at IOPS equals max. If any one of them fails to make a measurement, then we want to stop the IvyScript program. So in the next step, we want to rerun these tests, but we want to run at 90% of the IOPS that we measured the first time. So first of all, we're going to find the CSV file from the first 5 steps. So we create a file name string that consists of the test folder and then /all/ and then the test name, which is the name of the IvyScript file, and that's a built-in function, and this is a built-in function. And then we want to append .all equals all summary.csv. So this is a way that you can find the CSV file associated with a particular test step. Okay, so we'll generate that value and print it out. When we say set CSV file and we give it the name of the CSV file, we're loading it into an object that we can treat kind of like an Excel spreadsheet. You can access individual numbers in the CSV file by row and by column, and when you select the column, you can either provide the column number from 0, or you can provide a text string which is the column title header, and usually you don't know what column it's in. You use the column header. You can open one of the CSV files and you can pick out one of the column headers, and then you can paste it in your IvyScript program. The row number in the CSV file is the step number starting from 0. Okay, so here we repeat the loop we're doing for the fraction read equals 1.75.5, etc. And we're starting off at an index of 0. I should mention that this CSV file, the test folder /all, so this is the measurement summary all roll-up as opposed to the all roll-up in a particular test step. And then the all equals all summary.csv file has one line for each test step in it. Oh, by the way, the column titles are considered to be row -1, so that the row number corresponds exactly to the step number. So in this CSV file, row 0 is step 0 all the way up to row 4 being the 5th step. Okay. Now, here in this step, we're creating a variable called max IOPS. We declared it as a double up here, and we're setting the max IOPS variable to the CSV file cell value at index, and index here is the step number starting from 0, so we're going to start at -1 and then we increment it on each pass through. So index will hold the step number as we go through, and then we're retrieving from the overall IOPS column. A CSV file is considered to have text string column values, and so what we're doing here with this built-in function is we're converting the text string to a double precision floating point number. So this is how we extract max IOPS from a previous test step. We just find the CSV file and we pull out the row number corresponding to the step, and we pick the column according to the column title, overall IOPS in this case. So then we set all the workload threads to the total IOPS parameter, and I should mention here that for edit rollup, there's a special attribute called total IOPS, and it only exists in edit rollup. When edit rollup is executed, if there's a total IOPS parameter, what we do is we take the value of that parameter and we divide by the number of workload threads in the rollup instances specified on the edit rollup statement. So when we set total IOPS, we can have that number of total IOPS evenly distributed over all of the workload threads identified in the edit rollup statement here. In this particular case, we've selected a single rollup instance in a single rollup, but you could also say edit rollup MPU equals left brace 0, 1 right brace, so that you can send these parameter updates out to a set of rollup instances. And then within that, for the total number of workload threads inside the specified rollup instances, we divide total IOPS by the number of workload threads represented in the parameter here, and then the total IOPS value is divided by the number of instances and rewritten as IOPS equals. So when the edit rollup update hits the workload thread, it'll say IOPS equals a smaller number. And then we're setting fraction read to the fraction read value. So that's the part of how you automate workflows and you get results out of CSV files. And then we're going to pretty much run the same sort of thing. We're going to have a go to run a subinterval sequence. We're going to give it a name, and then we're going to have measure turned on. And we're going to be measuring a workload parameter, which means it works with a command device or without a command device. Again, we're going to measure the overall category instead of the random or the sequential category, etc. The accumulator type again is service time, but in this case, instead of looking at the count of the number of eyes posted, we're going to look at the average value in this accumulator. So it's the average value of the service time for the IOs that are posted that we're measuring here. And we want 95% confidence that we've made a measurement of the service time to plus or minus 2.5%, again with a timeout value. And here, I put max write pending change equals 20%. That's a pretty big number. So my note to myself here, it looks like we need to average over several write pending excursions to get the accuracy at 50% writes. So in some cases, the subsystem behavior may not be terribly stable. And at 50% writes, it looks like the subsystem was going up and down in write pending. So to get enough observations to actually measure the value of the service time at 50% writes, we had to average over a number of cycles of the write pending cycling up and down. So that's why in this case the max write pending change value was set to 20%. Okay, so having looked at the IVScript program, let's go ahead and take a look at the output. Let's I think I've loaded this actually into a spreadsheet. So here we can see that we loaded demo 5 measure read versus write RAID into this spreadsheet. Then we're going to look at the all equals all summary. We can see here I've made a graph showing the overall results of the test steps. There's 5 steps at IOPS equals max, and there's 5 steps at the 90% of the max IOPS. So in this case here, the vertical bars are showing on the left axis scale of the number of IOPS per FMD drive. So when I made this chart, I highlighted the columns which were IOPS per backend drive. And then the lines in this graph are the service time from each of these 10 steps. And what we can see is that at 100% reads, the service times to these FMDs is at about 0.5 millisecond, and then as you increase the percentage writes, the subsystem goes into emergency D stage, and it holds host IO back until there's room in write pending to put more data, and you can see that at high percentage writes, the service time climbs at IOPS equals max. And I've always felt that this chart wasn't fairly representing. So if we only look at the blue bars in this chart, the blue bars are what we normally report in our performance white papers. And we show, in my opinion, invalid numbers for the service time because we're running at IOPS equals max. And in real life, no user is going to be running at IOPS equals max. That would be considered a severe performance problem. So whereas I'd still like to traditionally, if to run the same kind of scalability tests as we run today, there's nothing wrong with showing the maximum IOPS that you can get. But I think what we should do in future is where we are showing the response time, or the service time, we should show that service time at 90% of the max IOPS. Because what you can see here is that when there is room in write pending to post data, we can see that reads are, we can see here that as we go to 100% writes, the service time actually gets better because the subsystem is accepting the data into cache, and then it's immediately telling the host that the I/O is finished, and it subsequently destages. So it's actually slightly faster to do a write than it is to read the data from an FMD. So you get this difference in the response time curve. So I thought that was very interesting. And now if we scroll up and we look at the, so here, let's, I usually do this on my 4K monitor, so these histograms are made a bit bigger. What we can see here is that by naming the steps, by giving the steps meaningful names, that we get nice meaningful tags on each of the lines in this histogram chart. Later on I went back and I updated the IVScript program so that it used a number with 0 digits after the decimal point. Later on so this chart was made a little bit earlier before I updated that. So if we go back to the left here, so all I wanted to say is the first 5 rows are the classic HDS scalability test where we run at IOPS equals max at a range of percentage reads. And then the second group of them, starting with 100% reads and going to 100% writes, are the results from running at 90% of max. So if we look at the service time histogram, what we can see for the reads is a little bit of a difference, but not a lot. And what we see with the reads is, yes, at 0.3 millisecond random reads from the FMD, we're getting a lot more IOs completing at 0.3 millisecond at 90% of max, but the general shape of the curve is very similar. If we move out to the test cases where there are significant numbers of writes, what we can see when we run at IOPS equals max is that we're getting some pretty high columns here that don't show up when we run at 90% of max. So to isolate those and make it more visible, I've made another histogram down here where I'm only showing the, I'm only showing the 100% writes case, or 0% read. And you can see here that there were a few IOs which completed at in the 200 millisecond range on the FMDs, and in fact that occurred all the time. But what we can see here very clearly is that when you're at emergency D stage, it looks like you wait for about 1 millisecond before there's room in cache for to complete the write IO, and so you see a big spike at this level. But when you're running at 90% of max IOPS and there is no holding back of the host IO until there's room in cache, you can see a very different profile there. Okay, so that was demo 5, showing you a workflow where we'll run one thing, we retrieve the output, and we use that to inform our decision about the next thing that we're going to run. That was demo 5. Thanks.